Let's talk about self-powering. There's two ways that you can have over unity. Let's talk about both ways. I'm going to compare this to a heat pump. Here I have my system. All right, I have my own input of energy, let's say in this system, that the operator inputs. Energy input by the operator, E-op. Okay, this system has some losses. I'm going to put my losses out on the bottom just as one little arrow. It's losing energy all the time in its inefficiencies. Let's say this is a pretty poor system. It's only 50% efficient. Like a heat pump is about 50% efficient. So all of the energy that's going into it from whatever source, 50% of it's going to leak away and escape, and I'm not going to be able to use. Over here now, I have the energy that's going out into my load and powering it, and this is going to be the work output. The actual work that I get from this system that I'm using. Now, if I have a system that nothing else puts any energy into it, this could be, for example, an electric motor. Here's my line energy that I connect and pay the power company for, E, operator input. Okay, I lose 50% of it down here. If I put in 1,000 joules of energy, I get 500 joules of work out, useful work in the load, and I lose 500 in the losses. This is the losses in the system. Every real system has losses if it's doing work and so forth. Every working system will have some losses. They can be made more efficient, yes, but they will have losses. They're not 100%. Well, that doesn't look so good. I'm not getting as much work out as I'm having to pay for energy. I'm only getting half out. This could be a heat. If this was a heat pump, it wouldn't be worthwhile putting in a heat pump. This is a heat pump when I lose the ability to use the atmospheric input and I have to go on to resistive heating. This is what I got. And it's only 50% efficient, and I'm paying through the nose for only getting out half of what I put in as useful work in the heat pump. But we don't do a heat pump that way. From the environment out here, there's heat energy and all this out here if we take it out. So we have a process which takes out some of that energy from that active environment. Let's call this the environment input. Now we have a different situation. Let's talk about how much total energy we have going in. We have two inputs of energy. We have the input that I'm paying the power company for. We have the input that I'm not paying for. I'm paying so little that let's consider this part of it is free from the environment, the heat energy I'm extracting from the environment. So I have these two energy inputs, and by the way, I extract a lot of the heat energy from the environment because I compress it and take a lot out. Well, isn't that interesting? Because now if I have 50% efficiency, I lose half of all the energy that goes through the system. Suppose I put in 3 parts. So I got 3 plus 1, I get 4 parts in here. I lose half of that, I get 2 parts out. This is a little bit of bad conditions for a heat pump. But I'm getting twice as much out as I'm having to put in. Now I'm not violating conservation of energy. That energy is actually being put in to cover these losses and cover the extra energy put out more than half of what I put in. The average home heat pump under good conditions produces 3 to 4 times as much energy out as actual useful work as what you have to pay for. The rest of it comes out of the environment. Okay, let's look at a particular example. I'm going to talk parts of energy. So everybody knows a part is a part. So if I got 1 part, that means something. If I got 10 parts, that means 10 times as much. Real easy. But I'm going to use 1 and 7. 1 part of energy I'm going to put in is electrical energy from the power line. I got to pay the power bill for that. No question, I'm going to have to pay for it. That's on the meter. And the meter's running. Okay, the environment, let's say, and it's a pretty well-designed heat pump, the environment's going to put in a good case, 7 times as much, 7 parts of energy that I'm going to get from the environment for free. So what's going into my system, 8 parts of energy. The total input to my system is the 1 that I put in and the 7 that the environment puts in. How efficient was the system? It was 50%. That means it loses half of everything going through it. That's 8 parts going through it. It's going to lose half. It's going to lose 4 parts. From the 8 going in and the 4 that I lost and I can't use, I have 4 coming out that I use as useful work. Okay, let's talk about the difference in efficiency and COP, because most engineers and even many practicing scientists don't know the difference. Efficiency is all the energy that's put into this system by any port, any factor at all. You divide that amount of energy into the amount of useful output you get. Output divided by total input is the efficiency of the system. What's the efficiency of this heat pump? I got one that I input, 7 parts that the environment inputs. That's 8 parts that's totally input to the system. And so the total input to the system is 8 parts. I divide the total input to the system by 8 parts by how much I get, that 8 parts, into how much I get out. 4 over 8 is 1/2, or we express that as percentage, 50%. So the efficiency of this system is 50%. It is not over unity efficiency. Never can you go past 100%. You always are less than 100% in any real system with losses. You can get a good generator that'll do 90%, but it darn sure will not do 150% efficiency. Now, COP is a totally different matter. COP only looks at one energy input and one only, and that's what you have to pay for as the operator. It doesn't care if something else puts in energy or not. It's defined as you take the total useful output you got, you divide that by the amount of energy you had to pay for. Doesn't matter what else got put in, just what you had to pay for. And that is your COP expressed as a decimal. Let's see what that is. 4 parts out, 1 part in, 4.0. My COP is equal to 4.0.